Okay, so here we go with part two. And we'll actually get into the lesson here. Hopefully those videos helped there and helped with what we were working on yesterday. So it says here that in the previous lesson, the instantaneous rate of change is equivalent to the slope of the tangent, right? And we know that a tangent is a line that touches a graph at one point. That is a tangent, okay? It touches a graph at one point. Also, the best estimate for the instantaneous rate of change occurs when the interval used to calculate the average rate of change is made as small as possible. So basically, on Monday, we talked about average rate of change. Yesterday, we talked about instantaneous rate of change. Calculating instantaneous rate of change, all you do is you do average rate of change, but you pick 2 points that are really, really close together. Okay? And we've been picking 2 points that are 0.01 apart, okay, or a hundredth apart. So what we're going to do here today, what we're going to look at is what we call a difference quotient. So we have if P, so a point P, I'll zoom in a little more here. So if point P, which we'll say is A and f of A, okay, our x value and our y value, and point Q is A plus H, okay, where H is any value, so we're just doing A, so our x value from P, plus some number, then our y value is f of A plus H. If these are 2 points on the graph, y equal to f of x, so any function, then the instantaneous rate of change of y with respect to x can, or at point P, can be estimated using this equation. So what we do is we do f of A plus H, which is basically our y2, minus f at A, which is basically our y1. And how we get this H value here, all divided by H, is because what we're doing is we're doing our x2 minus our x1. And in this case, our x2, if we look above, our x2 is A plus H, so A plus H. And our x1 is A, so we do minus A. These A's cancel out, and we're just left with H. So all over H. Okay? This is what we call the difference quotient. Okay? And the idea here is that H is going to be a very small number. Right? Something like H 0.01, maybe H is, right? H is typically a very small number. Okay? Now, if you look over here, right, this is just kind of giving a visual, right? It's saying that P and Q, P is a point on the graph where X is A and your Y is F of A. Q is another point on the graph, right? That's H away from A, right? Your X value is A plus H, okay? Now your slope of the tangent line is equal to the instantaneous rate of change. Now the idea when we're trying to find the instantaneous rate of change is we're trying to make this H value really, really small. This H value here really, really small, so that our second point is like right here, okay? Which makes your slope a much better prediction. Which makes your slope a much better prediction. Okay, your slope of the tangent line. Okay? All right. So this is our, what we call our difference quotient, and that's what we're going to use today. All this says here is this just says that the difference quotient represents the average rate of change or slope of a secant. It's the same idea, right? You're just finding the slope between 2 points, okay? The smaller the value used for H, the better the estimate. So like I said earlier, you could use 0.000000001 for H. That's going to give you a much better estimate than 0.01 for H. But we don't use something like this because it's it gets a little bit. You could just use smaller and smaller numbers. We picked 0.01 because we find that that gives a pretty good estimate for our purposes. Okay. So we're going to look at a couple examples here. Again, this isn't a long note; it's just a continuation of yesterday. But these two examples here should give a clear kind of picture of the idea here. Okay. So example one, we're looking at a specific function. We're looking at the function f of x squared. Now, in tomorrow's lesson, we're going to look at other functions that we've looked at throughout this course. Okay, we're looking specifically at the parabola today because it's kind of one of the foundational and simplest functions that we've looked at this semester. But you can do this stuff, rates of change, at average rate of change and instantaneous rate of change with every type of function that we've done this semester. Okay, so like I said in my previous video, our test will involve log functions, and so you will be calculating AROC and IROC using log functions. Okay, so that's just important to note, and in tomorrow's lesson we'll go over some examples of that. So it says to use the difference quotient to find an algebraic expression, okay, representing the slope of the secant line for the function f at x equals x squared from x equals 1 to any point h units away. Okay? So what we're going to do is I'm going to start by writing out my quotient, my difference quotient. So my difference quotient is, let's do this, a plus h minus f of a all over h. Okay? Now what I'm going to do is it's telling me that it wants me to focus on x equal to 1. Okay? So what I'm going to do is I'm going to sub in x equal to 1 for a. So I'm going to say, okay, f at 1 plus h minus f at 1 all over h. Now this question actually gives me a function. It's telling me that we're focused or we're using the function, the x squared function. So what I'm going to do here is I'm going to actually now sub these values, 1 plus h and 1, into my function. Okay? So that looks like this. So f of 1 plus h is going to look like this. Subbing 1 plus h into x squared is 1 plus h squared. Subbing 1 into x squared into my function, so we're subtracting it, is just 1 squared. Okay, so notice I sub each of the highlighted values into my function, all over h. We do not know what h is. We're going to simplify this now. 1 plus h squared simplifies to, well, I'm going to write this out, 1 plus h, 1 plus h, minus 1 squared is just 1, all over h. I'm going to FOIL these brackets. Okay. That's 1 plus 2h plus h squared minus 1 all over h. I just simplified, right? 1 times h and 1 times h simplifies to 2h. These 1's are going to cancel out. We're left with 2h plus h squared over h. I'm going to simplify. I'm going to factor out an h. We get 2 plus h all over h. I'm going to cancel out my h's, and I get 2 plus h. Okay? So this function here, this equation, this is equal to the slope of secant. Okay? Where h is how many units away we are from x equal to 1. Okay? So h, and it says up here, h is how many units away you are from x equal to 1. Okay? So what does that mean, right? How can we use this? Okay? Well, this, like I said, is an equation for our slope of our secant, and we'll look and read what B says. Part B says, use the expression above, the one that we just calculated, above derived from the difference quotient to find the average rate of change, so the A rock, or average rate of change is the slope of secant from x equal to 1 to each value. So it wants us to find the slope of the secant from x equal to 1 to 3. Well, let's go to our graph here for a minute. X equal to 1 and x equal to 3. Well, 3 would be like way up here, right? So it basically wants us to find the slope of this secant here. Okay. Well, the first thing we need to know is how far away is 3 from 1? What is this number here? Okay, how far away is it? And that's going to be our h value. Okay. So what we're going to do is we're going to say, well, h is just going to be 3 minus 1, the distance between these numbers, which is equal to 2. So if h is equal to 2, then my slope of secant is equal to 2 plus h, which is equal to 2 plus 2, which is equal to 4. So that's my slope of my first one, or my average rate of change in my first example. Okay. For the next one, it says that x is 1.01. So how far away is that from 1? Well, that's going to be our h. So 1 minus, or I guess no, we'll do it this way. 1.01 minus 1 is equal to 0.01. So I'm just going to find my slope. Now I'm going to write slope. Remember the letter m represents slope. So slope of secant we're going to write as ms. Okay? I'm going to add that up here. Ooh. Okay? Is going to be 2 plus 0.01, which is just 2.01. So our slope of our secant between those 2 points is 2.01. And for my last one, my h value, well, how far is 0.99 from h, or from x equal to 1, sorry? Well, it's going to be 0.99 minus 1, which is equal to negative 0.01. If I plug that into my secant, my slope of the secant formula, that's 2 minus 0.01, which is equal to 1.99. Notice that these two slopes are very similar, okay? Because our points are very close to 1. The question says here, describe what will happen to the slope of the secant as the interval from x equal to 1 to another point, h units away, progressively becomes smaller. So what if I picked a point what if I picked a point x equal to 1.0001, or x equal to 1.00000001, right? As I get closer and closer to 1. Well, what's going to happen is our value, our slope, our slope of our secant is going to get closer and closer to 2. Okay? And all this means is it's going to become, so it's going to we'll say the slope of the secant is going to be a better and better estimate for the IROC, the instantaneous rate of change, at x equal as we get closer and closer and closer to 1, we're going to be making a better and better and better estimate for the instantaneous rate of change at 1. And you'll notice just based on those two values there, 2.01 and 1.99, that we're going to be closer and closer to 1. Okay? Let me just check and see on my time here. Should have a timer going on my phone on the side here, but I did not do that. 15 minutes. That is perfect. We will be another 10 here probably. Okay? Hopefully this is making sense. All right? Again, the best way to actually make sure this is making sense is to do questions. Okay? So once we complete this lesson, please take some time to try some questions. It is the best way to make sure that you know this stuff. Okay? All right, this one here, tennis. I love tennis. A tennis ball is tossed straight up. Okay? Right? Typically, that's what you do if you're serving the ball. So I throw the ball straight up into the air before serving it. So a tennis ball is tossed straight up. So the position, S, so it's position, and we're going to represent that with the letter S, in meters at time t in seconds, is given by this equation. Okay? It's telling us here to estimate the instantaneous velocity. Now remember, velocity is just the rate of change. Okay, so velocity is just rate of change for distance time questions of the ball at 1 second. All right, okay, fair. So what we need 2 points to estimate this velocity. Now, it's asking us for instantaneous. So when we want instantaneous, we want 2 points that are very close together. So we're going to pick 2 points here. I'm going to choose, well, the one that we're given, t equal to 1, and I'm going to choose t equal to 1.01. Okay, 2 values that are very, very close together. Now what I need to find, so if I'm thinking of this as a coordinate, right? Oh, that's a bad one. If I'm thinking of this as a coordinate, I need my y values. In order to find my y values, I'm going to plug those x values or t values into my equation. So plugging those into my equation, I'm going to get, so we'll say s of 1 is equal to 20 bracket 1 minus 5 bracket 1 squared. That's basically 20 minus 5, which is 15. Just make sure I have my answers here. And if I sub in t of 1.01, that's going to be 20 bracket 1.01 bracket minus 5 bracket 1.01 squared. That's equal to 15.0995. Okay? So I now know my y values. I'm just going to need more space for this one, which I knew I was going to. 15.0995. And now, if I want to find slope, all I do is I determine my, so we'll say I rock, my instantaneous rate of change, or velocity, is equal to y2 minus y1 over x2 minus x1. Remember, you can label these x2, y2, x1, y1. It doesn't matter which way you label them. If I said these were x2, y2, and these were x1, y1, you still get the same solution. Okay, 15.0995 minus 15 all over 1.01 minus 1 equals 9.95, and that's going to be meters per second. Okay? So the instantaneous rate of change is approximately 9.95 meters per second. So the velocity, we can say the velocity at 1 second is approximately 9.95 meters per second. Okay? The next question, and this is our last question here, does ask us to use the difference quotient. You will be asked to use the difference quotient on your test to determine a simplified expression, okay, at times. Now, this one says use the difference quotient to find the instantaneous rate of change at t equal to 1. What we're going to do is we're going to use the difference quotient. We're going to simplify into just a simple expression. And then what we're going to do is we're going to sub an h value into that expression, okay? So our difference quotient, what color do I want to use here? Let's go with green. Okay. So our difference quotient, I'll just call it DQ for now. And all I think of when I say DQ is Dairy Queen. So it's making me hungry for ice cream. Minus f of a all over h. Okay. Now, in this question, it's telling us our value that we're focused on. So this is going to be our a value is 1. So I'm going to sub in. I'm going to say, okay, well, f of 1 plus h minus f of 1 all over h. Now remember that f of 1 plus h just means write the function, but sub in 1 plus h wherever I see x. So this is going to be, where's my equation? I just need my equation here. So my first part, I'm going to put it all in brackets here. So it's going to be 20, my t, right? T, so I'm going to sub in 1 plus h, close brackets, minus 5, bracket 1 plus h squared. Okay, so that's the function when I sub in 1 plus h. Now I'm also going to write the function, so I'm going to subtract the function when I sub in 1. So that's going to be 20 bracket 1 minus 5 bracket 1 squared. And this is going to be all over h. Now all we want to do here is we want to simplify this. This looks quite, this may look hopefully not too intimidating, but we do want to just simplify this expression here. So first part here, I'm going to multiply my 20 into this bracket. So I get 20 plus 20h minus 5. I'm now going to expand this bracket here to get what I get in here. So now I'm just going to do, you could just write this as 1 plus h, and FOIL it. Okay. So that will be 1 plus 2h plus h squared if I FOIL that. Now, because there's nothing in front of this bracket, I'm removing the big bracket here. I'm removing these big brackets because there's nothing in front. Notice with this big bracket here, I have this negative sign out front. So I am going to want to distribute this negative into this bracket before I remove that bracket. Okay. But I'm not even going to bother doing that just yet. To start, all I'm going to do is I'm going to simplify what's in that bracket. So it's going to be minus 20 times 1 is 20, minus 5 times 1 is just 15. All over h. Okay. Now I'm going to simplify. I'm going to multiply this negative 5 into this bracket, and I'm going to multiply this into the bracket. I get 20 plus 20h minus 5. Minus 10h minus 5h squared minus 15 all over h. We're going to swing this up over here. I'm going to group my like terms. So 20 minus 5 is 15. Minus 15 is 0. So those terms actually quite nicely all disappear. 20h, so minus 10h is 10h. So I have 10h minus 5h squared all over h. I'm going to factor out an h, so I get 10 minus 5h all over h. My h's cancel out. I'm left with 10 minus 5h. And this is an expression for the slope of the secant. Okay? So this is what we call our slope of our secant. So we can call this ms or our IROC. Okay? Or we can say IROC. All right? So that's what that's equal to. So now, remember it was saying to estimate it at 1. So typically what we'll do here is we just want to pick an h value that's very small. Okay? So typically we're choosing h values of this one right here. Unless otherwise stated, I would always choose an h value of 0.01. Okay? Unless I say otherwise. So sub that into your equation. So we get 10 minus 5 bracket 0.01. And if I do that there, I get 9.95 meters per second. Now notice that that value is equal to this value. Okay? Same thing, done two different ways. One using the difference quotient. The thing about the difference quotient is that it kind of allows you to pick different values. Okay? Now, the last thing that I do want to point out, okay, and actually notice that in the homework it says use the difference quotient approach and find an instantaneous rate of change. So please do that in those homework questions. That's your homework there. One thing that I do want to point out, okay, is that I'm just going to rewrite this over here. So we have 10 minus 5h. If h, remember, we're choosing h values that are really small, right? 0.01, for example. As h gets smaller and smaller and smaller, it's going to become closer and closer and closer to 0. Okay? Right? For example, h could be 0.01, h could be 0.001, h could be 0.00001, h could be 0.00000, and I could keep writing zeros forever and ever, 1. That number is getting closer and closer to 0. Your best estimate is basically going to be when h is 0. If h is 0 in this expression, what is our instantaneous rate of change? Notice that our instantaneous rate of change is 10. Okay? So the difference quotient actually allows you to solve for the exact rate of change at a specific point. Okay? By subbing in 0 for h. All right? We're going to end there. Try the homework questions. I will hopefully see you very soon. Things are good. So we'll see you all soon. If you have any questions, please send me an email and have a great rest of your day. All right. Talk to you all later.